Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, we start our chapter 4 in analysis of flow in pipes. Okay, learning outcome. So at the end of this chapter, students should be able to understanding of laminar and turbulent flow in pipes and the analysis of fully developed flow. Calculate the major and minor losses associated with pipe flow in piping networks. Understand and difference velocity and flow rate measurement technique. Okay, 4.1 characterization of flow based on Reynolds number. Okay, Osborne Reynolds, a British engineer, conduct a flow experiment using this. Okay, by injecting dye into a pipe flow. Okay, using this into pipe flow to classify the types of flow. So he inject the dye here to flow in this pipe. So we can look at the result, the near laminar, and using this is a turbulence here. So this is the flow. Okay, so laminar and turbulent flow. So look at this concept, flow regimes of candle smoke plum. Okay, at this stage is a laminar flow and at this stage is turbulent flow. Okay, actually laminar is a smooth streamlines and highly ordered motion. Okay, turbulence is a velocity fluctuation and highly disordered motion. Transition is the flow fluctuates between laminar and turbulent flow. Most flow encountered in practice are turbulence. So the behavior of colored fluid inject into the flow in laminar and turbulent flows in a pipe. So look at this. So when the dye is traced in this pipe, so we can know that this is laminar flow because this is smooth line. Okay, when this is have the fluctuated highly disordered motion, so this is turbulent flow. Okay, three types of flow. We can look at the laminar flow. Okay, so as a smooth line here. Okay, transitional flow, they have a smooth line and the fluctuates. And for the turbulent flow is more than fluctuate the line here. So we use the Reynolds number at this equation. These equations. Reynolds number is equal to density times by velocity times by diameter divided by dynamic viscosity, or velocity times by diameter divided by kinematic viscosity. So we look at when the laminar flow, Reynolds number is less than 2000. Less than 2000. When the transitional flow is Reynolds number is between 2000 and 4000, but for the turbulent flows more than 4000. Okay, so look at this using the Reynolds number here. So we use this equation. Reynolds number is equal to density times by velocity times by diameter is equal to viscosity, or diameter times by velocity divided by kinematic viscosity. So from this Reynolds number, we can state the flow based on to find the laminar or turbulence or transitional. Okay. So example 1. So we look at the question. Okay, determine the range of average velocity of flow for which the flow would be in transitional region if an oil Sg is 0.89 and dynamic viscosity 0.1 Nm per meter square is flowing in a 2-inch pipe. Okay, so this is inch pipe. Okay, for transitional flow, the Reynolds number is between this 2000 to 4000. So we find the Reynolds number here. Okay, when Reynolds number is 2000, so the velocity is 4.424 meter per second. Okay, when the Reynolds number is 4000, so we get the velocity is 8.847 meter per second. So you must convert the 2-inch pipe to meter. Okay, convert the inch to meter. So therefore, for the flow to be in transitional state, the average velocity V should be between 4.4 to 4 meter per second and 8.847 meter per second. Okay, look at the friction. This is the friction in pipe. Okay, there's a friction in this is the pipe here. Okay, so the L is the length. Okay, when fluid flows in pipe conduit, shear stress will be occurred. So velocity in pipe will be decreased because of energy loss that can be measured by pressure difference. HF is the height of friction. Okay, friction in pipe, we use the symbol of HF. Okay, so this is the friction in pipe. By measuring the difference of pressure with known length L. Okay, from the chart figure shows the result. Okay, when the lamina, so look at this line here. Okay, this is for lamina, this is for the transitional flow, and this is for turbulence. So for turbulent flow, N is equal to 1.75 for rough wall pipe, N is equal to 2 for smooth wall pipe. Okay, this is the coefficient for N. Okay, so we use the Bernoulli equations as in chapter 3. Okay, so in this chapter, we also use the Bernoulli equation. So figure shows total head measure from that term. Okay, they have using the Bernoulli equation, but you must plus the friction loss, so head loss. So head loss is also called the friction loss. Okay, HL can be minor or major head loss. Okay, so just the equation. Okay, most equation that you must know in this chapter, you must use the Bernoulli equation. Okay, so energy head loss, okay, can include the major head loss, HF. Okay, major head loss can use the HF. Okay, this is the friction head loss occur along the pipe. Okay, this occur along the pipe. Okay, this is occur losses due to the friction along the pipe. But for the minor head loss, HM, normal flow disruption occur in entrance, submerged discharge, contraction, expansion, pipe fitting, bends, and elbow. So this is called minor head loss. Okay, so friction in pipes of constant cross section. Okay, head loss or energy loss in pipe flow may be caused by friction, valve fitting, expansion, and contraction in pipe diameters, and others. Frictional head loss is known as the major head loss. Okay, HF. Okay, the major head loss in pipe flows as the loss occurs along the pipe, while other head losses such as dual valve fittings, expansion, and contraction are known as minor losses. Okay, this is minor losses. Minor losses due for valve fittings, expansion, and contraction. Okay, frictional head loss is known as the major head loss along the pipe. Okay, so friction head loss can be estimated using the Darcy-Weisbach equation. So we use the HF is equal to FL V squared over 2G. Okay, so this is the equations for head loss. Okay, for laminar flow, the head loss due to friction can be also estimated using the Hagen-Poiseuille equation. Using this HF is equal to 32 times by viscosity times by length times by velocity, okay, divided by the specific weight times by diameter power of 2. Okay, this is the H. Okay, so for laminar flow, the friction factor F can be calculated based on Reynolds number. Okay, this Darcy-Weisbach equation HF FL V squared over 2GD. This is for the Darcy-Weisbach equation. For Hagen-Poiseuille equation, so we use this equation. So no need to worry, all this equation is given in your final or in your test. So until using the both equations, so we get the F is equal to 64 times by Reynolds number to find the F. Okay, friction factor, laminar flow. Okay, for F here. So formula Darcy-Weisbach using the HF is equal to F times by L over D times by V squared over 2G. Okay, this is the equations to find the HF using the Darcy-Weisbach. Okay, for using the formula Hagen-Poiseuille, so this formula used only for laminar flow. Okay. Equation shows that in laminar flow, the loss of head is proportional to the first power of velocity. So in laminar, the friction is independent of the roundness of the pipe but depends on viscosity and density. Okay, so look at example 4.2. Okay, so in a refinery oil with the Sg is equal to 0.85, viscosity 1.8, okay, power 10 of power minus 5 flows through a 30 meter long 100 mm diameter pipe of 0.5 liter per second. Okay, the Q. So is the flow laminar or turbulent? Find the head loss per meter of pipe length. Okay, so we use the Reynolds number here. Reynolds number is equal to velocity times by diameter divided by viscosity, because in this question they give you the viscosity, kinematic viscosity. So we use this equation, Reynolds number, put all the parameter value here, and you get the Reynolds number is less than 2000. So therefore, this is a laminar flow. After you get the Reynolds number, so you must find the velocity in this pipe. So you use these equations. Velocity is equal to Q over A. So we get the velocity 0.0637 meter per second. Okay, after we get this one, so we use the F is equal to 64 over by RE, because this is laminar. Okay, remember that this flow is laminar, so automatically you use this equation to get the friction factor F. So you get the 0.1810 for F. After we get the F, so you just put the F to this equation. Okay, head loss per meter pipe length using the HF here. So we get the HF in this pipe 3.74. Okay, times by 10 power of -4 meter. So we get the HF, okay, head loss per meter of pipe length. Okay, at this stage, okay. So we look the example 4.3. So using the Hagen-Poisson equation, determine the difference of pressure between two cross sections. Okay, to find the difference of pressure between two cross sections. Okay, point A and point B. Okay, this is the values given in the questions. So M is when mass density, okay, D, okay, the 300 mm, you convert to 0.3 meter. L is the length of the pipe. ZB minus by ZA is a height of the point A to the point B. And this is the velocity. Okay, so we use the Q is equal to M mass over density. So we get the Q is this equation. Okay. Okay, use this to find the Q. So from the Q here, you find the velocity. Okay, velocity is equal to Q over A. So we get 0.053. So we get the velocity value here. And just put the value to the Reynolds number. Okay, this is just viscosity. Okay, write in your notes, just correct here. This is the viscosity here. So we get the, so using the Hagen-Poisson, so you must use this equation to using the Hagen-Poisson. So you just put all the value here to these equations. So we get the HF is this one, 18.27 meter. So after that, you must use the Bernoulli equations. Point A to the point B must plus the HF because this is the friction loss in the pipe. Okay, so you must plus the HF here. So you just rearrange the equations here until you get the PA minus by PB divided by rho G is equal to 40 plus 18.27 here because this is HF here. So we get the difference pressure is 5.43 kilonewton per meter square. Okay, so we get the value here.